Alright everyone, welcome back. Today we're going to cover probably the most important topic of the whole semester. This is where we go back full circle and where all of the ideas that we have learned so far kind of come up together, kind of like when you go on a trip and come back home. So we're bringing it back home now with the fundamental theorem of calculus. As the name suggests, is probably what I would call the main idea of the course. This is what we have been building up to over the past weeks in the semester. Now, so far we have been talking about differentiation, and that was introduced when we did the problem with the tangent line, finding the equation of the tangent line of a function at a particular point. The tangent line gave us using the derivative, we could get the slope of the tangent line at a particular point. Now, after we spoke about the rules of differentiation, we spoke about the antiderivative, and we saw that the antiderivative, or the integral, has to do with a problem of area, finding areas under the curve, as we saw last time with the definite integral and with Riemann integration, the Riemann series, Riemann series, not Riemann integration, Riemann series. Now, although we had been working with the tangent line problem and the integral problem, the area problem, these two problems are actually related. And I mentioned this last time, but I'm going to mention it again. The antiderivative in it. So the fundamental theorem of calculus, in simple terms, says that the derivative and the integral are inverse operations of one another. And let me be more specific, the definite integral are different operations of one another. Now, the fundamental theorem of calculus will tell us the following. So this is the fundamental theorem of calculus. I always say that whenever you get to a class and you hear the word fundamental theorem, that's probably the thing that you should remember the most about the class. So this is the theorem that you probably remember the most from this class. Okay, so it says the following. If a function f is continuous on the closed interval AB, and capital F is an antiderivative of f, little f, on the interval AB, the same closed interval, then the following is true. Then the integral, definite integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So this is giving us a way of actually evaluating the definite integral without using the limit processes that we were using in the previous section. Remember, in the previous section we used the Riemann integral and took a limit of it to be able to find the exact solution of a definite integral. But this is now giving us a much easier way of solving for definite integrals, provided that the antiderivative exists. So let me just write that down. This theorem gives us a nice way of solving definite integrals without needing to use the limit of a Riemann sum, which is what we did in the last section. Now, let me give you some guidelines and then we'll do some examples of how to actually do these calculations. So, number one, and this is all provided, so let me say the following: provided an antiderivative exists, can be found. Let's put it that way. There are some antiderivatives that in this class cannot be found easily. There's some special cases. You may see those special cases either in the next section or in Calculus 2. In any case, number one, when you apply the fundamental theorem of calculus, the following notation is very useful and it's very standard. It's very standard. So let's say somebody gives you the integral from a to b of f of x dx. Let's say you actually find out what that antiderivative is. So we write the antiderivative is f of x, and we are going to evaluate it from a to b. So what we did was we dropped the integral sign because we found the antiderivative, but to remind ourselves that we still need to solve for f of b minus f of a, as the theorem says, we write this right close bracket and write the limits of integration from a to b. And this is equal to, again, f of b minus f of a by the fundamental theorem. So this notation helps us remember that we have to still solve for the difference of the function evaluated at the limits of integration. For example, let's say somebody comes up to you in the street and they give you the following integral. They give you the definite integral from 1 to 3 of x cubed dx. We know, they recall, so let me just remind you, when you have the integral from x to the p dx, this is equal to x to the p plus 1 divided by p plus 1 by the reverse power rule plus c. So here, this is equal to x to the 3 plus 1, which is 4, divided by 4. And because this is a definite integral, I'm evaluating this from 1 to 3. So now, in this problem, capital f of x is equal to x to the 4 over 4. And I'm going to be plugging in 3 and 1. So that's what's going to be happening here. I'm going to do f of 3 minus f of 1. But f is x to the 4 over 4. So this is the same thing as 3 over 4 minus, and it's always good to use parentheses because of this negative sign in the middle. It helps you keep your work organized. So minus 1 to the 4 over 4. And this is equal to, well, 3 cubed. Last time I checked, that's 83 cubed. 3 to the 4 is, last time I checked, that's 81, because 3 times 3 is 9, times 3 is 27, times 3 is 81. So we have 81 over 4 minus 1 over 4. Well, 81 minus 1, that's 80 over 4. And 80 over 4 is equal to 20. Yeah, 20. Let me break this up. Okay, so this is the solution for this antiderivative. Notice that there's actually pretty light work compared to the limit problem that we had to use before. Before we would have to actually find out a way of expressing this using the definition of the Riemann sum, and then take the limit as delta x goes to infinity, and that can prove to be very difficult and very time consuming. I think we did the last example we did was like over half an hour long. So this notation is very convenient. Now, the other thing that you should realize is that when we defined the antiderivative a couple of weeks ago of f of x dx, we said that was equal to the antiderivative of f of x plus c, but I did not write any plus c's in here. And the reason for that is as follows. So first of all, it is not necessary to write a plus c here when you have a definite integral. So it is not necessary to include a constant of integration c in the antiderivative, because of the following. So when you take the antiderivative of the definite integral from a to b of f of x dx, that is equal to capital F of x evaluated at f of x plus c evaluated at a and b. But now, if we actually do this evaluation, what we have is f of b plus c minus f of a plus c. And what's going to happen? Well, here we have f of b plus c, but here we have minus f of a and minus c, because you distribute the negative sign. So I said this plus c and this minus c are going to cancel out, and you're just going to get negative f of b minus f of a, which is the fundamental theorem. So this is the fundamental theorem of calc. So this is, again, if you don't remember anything else that we did the whole semester, this is probably the one thing that you should remember. There's a reason why it's called the fundamental theorem of calculus. Okay, let's do some more examples. So let's say somebody tells us to evaluate the following definite integral. So evaluate the following definite integrals. Right, so say somebody comes up to us and gives us the integral from 1 to 2 of x squared minus 3 dx. Okay, well, first thing we could do is find the antiderivative term by term. So remember, we can do this. We could first separate the antiderivative and find the term by term. This is probably the only time that I'm going to do this in these examples, but I want to remind you that we can do this, and so oftentimes it is useful to separate the integrals. So this still applies for definite integrals. You could still separate it. Okay, so what is the antiderivative of x squared dx? Well, again, by the reverse power rule, this is going to be x cubed over 3 evaluated from 1 to 2. Remember, I could pull out that 3 to the outside, so instead of writing it here by the constant multiple rule, I could write it out here. And if you remember, the antiderivative of 1 dx is just x, because it's like there's an x to the 0 power there. Remember, anything to the 0 power is 1, and then when you add 1 in by 1, you just get back x to the first. So this is minus 3x, also evaluated from 1 to 2. Now, because I'm evaluating this whole thing from 1 to 2, I could just rewrite it as 1, x cubed over 3 minus 3x, all evaluated from 1 to 2. And again, you could have done this in one step, but I just want you to remind you that you could split the integral. Okay, so now when you apply the fundamental theorem, remember, you're going to do f of b divided by f of a. This is b, this is a. So you're going to plug in 2 wherever you see an x, and then 1 wherever you see an x. So it's going to be 2 cubed over 3 minus 3 times 2. That's for the, this is the f of b piece, minus, that comes from the formula, and then, or from the theorem, and then f of a. So f of a is 1 cubed over 3 minus 3 times 1. And then you could simplify. So we have 2 cubed, that's 8. We have 8 over 3 minus 3 times 2 is 6, minus 1/3 plus, let me distribute the negative sign, 3. So now what we have here is 8 over 3 minus 1 over 3, that's 7 over 3. Negative 6 plus 3 is negative 3. And then to make this denominator is the same, you multiply top and bottom here by 3, so you have 7 over 3 minus 9 over 3. And this is equal to negative 2/3. So we have that the antiderivative from 1 to 2 of x squared minus 2 dx, which is what we began with, all the way up here, minus 3, not minus 2, is equal to negative 2 over 3. All right, so let's do another one. Let's evaluate another one. So this time we have the definite integral from 1 to 4 of 3 times the square root of x dx. Now, much like before, the first thing you should do is to rewrite this. So this is equal to the definite integral from 1 to 4 of 3x to the 1/2 power, because remember, the square root is the same thing as the power half, same thing. Okay, so when you take the antiderivative of this, what do you get? Well, remember, you have to add 1 to the numerator and 1 to the denominator. So before I do that, let me just take out that 3 so you can see it better. This x to the 1/2 dx. Now I'm only worrying about this piece. So we're going to add 1 to the exponent, and then in the denominator we're going to have 1/2 plus 1. So if you add 1 to the exponent, that's going to be 3/2. Remember, to have fractions, you have to have the same denominator. So when you make this denominator is the same, you're going to multiply by 2's. So you're going to have 3 times the following. You're going to have 3 times x to the 3 over 2 over 3 over 2, evaluated from 1 to 4. Notice that I dropped the integral symbol because this is the antiderivative. So once you find the antiderivative, you drop the integral sign. And I'm putting these brackets because I took out the 3, and I have to multiply by 3 once I evaluate this definite integral. So once I do the fundamental theorem of calculus at the end, I'm going to multiply whatever I get times 3. In any case, let's simplify this a little bit. X to the 3 over 2 divided by 3 over 2 is actually the same thing as 2x to the 3 over 2 divided by 3. And I'm evaluating this at the points 1 and 4. The values 1 and 4. So, by the fundamental theorem, this is equal to 2 times 4 to 3/2 divided by 3 minus, this was again by fundamental theorem, I add another parenthesis to emphasize, so this is f of b, and then minus 2 times 1 to the 3 over 2 over 3. And this is your f of a. Okay? So now you have 4 to the 3 over 2. So what I like to do when you have something like this is first take the square root and then cube it. So this is going to be 8 because the square root of 4 is 2, and then when you cube it you get 8. So we have 3 to the 2 times 8 over 3 minus 2 over 3, because 1 is just 1 when you square it, and then when you find the cubic root you just get 1. So we're going to have, and notice that I'm going to have a 3 in the denominator, so I could cancel the 3 out right away, but I'm not going to do it right away. So 2 times 8 is 16 over 3 minus 2 over 3. So this is equal to 14 over 3. And then you multiply by 3, the 3 so cancel out, so you get 14. So I have that the integral from 1 to 4 of 3 radical x dx is equal to 14. Okay. So another one. Say somebody gives you the antiderivative from 0 to 4, from 0 to pi over 4 of secant square x dx. Okay, so here you got to remember the rules for differentiation. So like I mentioned in the previous video, I always begin by writing the rules of each trigonometric function, because they may come up, so you might as well have them. So the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant square x. So usually I write all of this down before I begin a problem with a trigonometric function, because they may come up. So you might as well have them handy so that you don't panic. If this was definitely an in-class exam, I would recommend that, so you don't panic and forget what they are. In any case, we can clearly see what the antiderivative of secant square x is going to be. It's going to be tangent x. So we can right away simply solve it. So the antiderivative of secant square x is going to be tangent x. And we're going to evaluate that from 0 to pi over 4. Now, you may have to pull out your reference triangles for pi over 4 or the unit circle. But in any case, we plug in tangent of pi over 4 minus tangent of 0. It turns out the tangent of pi over 4 is 1. And tangent of 0 is 0. You can see the tangent of 0 is 0 because tangent is sine over cosine. Sine of 0 over cosine of 0 is going to be equal to 0 over 1, so that's 0. And tangent of pi over 4, if you use the reference triangles, you're going to get the tangent is 1, because you're going to have sine of pi over 4 divided by cosine of pi over 4. If you turn those radians into degrees and use the reference triangles, you'll see that there's going to be 180 divided by 4, which should be 45. So you're dealing with the 45, 90 triangle. And you'll see that when you do the appropriate substitutions for sine and cosine of 45 degrees, doesn't matter which side you pick, you're going to get 1. So the solution to this is 1. Notice that we use a couple of facts from pre-calculus, especially reference triangles or the unit circle. So this one was much easier in that sense if you recall these facts from pre-calc. If you don't recall those facts from pre-calc, it may be more challenging. But this is definitely better than taking the limit of a sum by far. Okay? Let's do one involving the absolute value. I believe this is 4. So let's evaluate the integral from 0 to 4 of 2x minus 1 dx. First of all, let's remember what the absolute value graph looks like. The absolute value of x graph looks like this. This is y equals absolute value of x. It's like a V. So this one, 2x minus 1, if we were to graph this, remember that to graph it, we have to find the vertex, and to find the vertex, we find the value for which the inside piece is equal to 0. So that's 2x equals 1, which means x equals 1/2. So that means, let's say this is 1, this is 1/2. That means that this graph that we're dealing with looks like this. It looks almost identical to the other one, but it goes up like this. It has a vertex at 1/2. It crosses, you could find out where it crosses the axis here at 1. And you could find out obviously other points in there. So the blue line corresponds to the problem that we're looking for. Now keep in mind that the absolute value function as written is not differentiable because of the sharp corners. For the same reason, you cannot straight up find the antiderivative of it. So what we have to do is use the definition of the absolute value. So remember that the absolute value of x is equal to a piecewise function minus x if x is less than 0, and x if x is bigger than or equal to 0. But what makes our original piecewise function 0? X equals to 1/2. So we get that the absolute value of 2x minus 1 is the same thing as negative 2x minus 1 if x is less than 1/2, and 2x minus 1 if x is greater than or equal to 1/2. That is by the definition of the absolute value. So whenever you're dealing with absolute value, you could do this. You could break it up into a piecewise function. So that's what we're going to do with this antiderivative now. We are going to deal with it as a piecewise defined function. And we did this when we were talking about the indefinite integral. So now we have the integral from 0 to 2 of 2x minus 1 dx being equal to the following. It is equal to the integral from 0 to 1/2. Remember that theorem that we had where we could divide the interval into subintervals? We're going to apply that here because now we have a cutoff point for our piecewise function, which is 1/2. So we're going to go from 0 to 1/2 when we are negative 2x minus 1, so negative 2x minus 1 dx, and we're going to add from 1/2 to 1 the other one, which is 2x minus 1 dx. Okay. This is terrible board use given that I have an infinite amount of space on this side. Sorry about that. So anyway, this is equal to the antiderivative of from 0 to minus 1/2 of negative 2x plus 1 dx plus the interval from 1/2 to 1 of 2x minus 1 dx. So let's work on these. I'm going to get the antiderivative at the same time, and then we're going to apply the fundamental theorem also at the same time. So let's see how we do. So the antiderivative of negative 2x plus 1 is going to be negative 2x squared over 2 plus x, and we are going to evaluate that from 0 to 1/2. Again, this is using the reverse power rule, plus this is going to be 2x squared over 2 minus x, and we're evaluating this one from 1/2 to 1. Again, reverse power rule. There's some cancellation, as you can see. Let's cancel those 2's out. So we're going to get negative x squared plus x from 0 to 1/2, and x squared minus x from 1/2 to 1. And now we can apply the fundamental theorem on both of them. So I'm gonna use blue for this one and red for this one. So for the first one, I have negative 1/2 squared plus 1/2 minus 0 squared plus 0. Again, this is my f of b minus f of a, and that's for this first one. And then I have a plus from here, that middle plus. And then I have my other expression, which will be 1 squared minus 1. And then this is minus 1/2 squared minus 1/2. Okay, so let's solve. Okay, minus 1/2. Okay, 1/2 squared is just 1/4, and minus 1, that's just minus 1/4. So I have minus 1/4 plus 1/2. This is just going to be 0, so I don't have to worry about it. Plus, now 1 minus 1, that's going to be 0. 1 squared minus 1. 1 squared is 1, minus 1 is 0. Then I have minus, so instead of a plus, let's put a minus here. 1/4 squared, 1/2 squared is 1/4, I meant to say, minus 1/2. This is what we have so far. So here, instead of figuring out, let's add this and this, instead of doing that, there's something that you can easily do. Just write like terms together. So we have minus 1/4, and then here we have another minus 1/4. Then here we have a plus 1/2 on the left side, and then on the right side we have another plus 1/2, because minus is plus. So we have negative 1/4 and negative 1/4, that's negative 2/4. 1/2 plus 1/2 is 1. Notice that negative 2/4 is just 1/2, negative, and 1 minus 1/2 is just 1/2. So we get that the solution is 1/2. Okay. Oh boy. I just realized I messed something up. This is correct for from 0 to 1, but we were supposed to do it from 0 to 2. So I am going to just shamelessly switch this to 1. We're supposed to find the area up to 2, which should have been here. But we found it up to here, and I don't feel like doing that again. So this area is correct for that particular problem. It's equal to 1/2. Okay, let's do one more, since I just brought up the idea of finding area using the definite integral. So this is example number 5, if I'm not mistaken. So let's find the area of the region bounded by the graph of y equals 1 over x, the x-axis, and the vertical lines x equals 1 and x equals e. Okay, so first of all, let's get an idea of what's going on here. We were asked to find some area for a function that for a space that's bounded by a function, the axis, and 2 lines. So all this just come out to, let's see, so we have 1, 2, 3. This is my x-axis. Let's say up here I have 1 and 2. Now remember, the line of the graph of 1 over x has a vertical asymptote at 0, and it kind of looks like this. Okay, when you graph it on both sides, it looks like this. Now the area that we're interested in is the area bounded by the lines x equals 1, x equals e on the x-axis. So that will be x equals 1 right here. E, Euler's number, is between 2 and 3, so that will be this line right here, and the x-axis right here. So that will correspond to this area right here, for that shaded area. So that's what we're looking for as far as the area. Now notice that the values of y are positive on the interval 1 to e. So from here to here, all of our values are positive. So we don't have to worry about getting a negative solution for our area. And like we mentioned before when we discussed the definite integral, we can use the definite integral to find the area. So this area is equal to, well, the limits of integration are my a and b. So where does my closed interval begin? My closed interval begins at a equals 1 and ends at b equals e, if you look from left to right. So I have 1 to e here. What is my function? My function is y equals 1 over x, dx. So this is what I'm trying to find the area for in this closed interval. Now, we haven't learned yet how to solve problems like this, but we do know what the antiderivative of this is. We don't have to think too much about it, because if you recall from way back when we were doing differentiation, y equals ln of x, the derivative of this, y prime, was 1 over x. So we have an antiderivative for this. So we have that the antiderivative of 1 over x dx is ln of x, and we're evaluating that from 1 to e, which means that by the fundamental theorem of calc, that stays f of b minus f of a, I'm going to have ln of e minus ln of 1. Well, the ln of e, you should remember, this is the one-to-one property of the natural logarithm. This is 1. They're inverses of one another. And ln of 1, you remember what that is. The graph of the ln function looks like this, and it is 0 at 1. So it's 1 minus 0, which is 1. So we have that the area right here, let me call this R, this bounded region, is 1. So area is equal to 1. And that is how you solve problems using the definite integral. That's how you find area under a curve using the definite integral. When you get to calculus 2, and actually even in the rest of this section, where we're going to continue to talk about area, but when you get to calculus 2, you will find out how to find area of more complicated figures. But this all stems, at the end of the day, of using the fundamental theorem of calculus. What you will learn in calculus 2 is techniques of how to solve more challenging integrals than this. Okay, so I'm going to end this part here. When we come back, we're going to talk about the mean value theorem for integration. We're going to talk about the second fundamental theorem of calculus, and if time permits, well, time should permit, I'm recording this, the net change theorem. So all these theorems are also very important for your final exam. The most important ones are the fundamental theorem and the second fundamental theorem. But the other theorems that I'm going to speak about may come up in other courses, especially if you continue to study mathematics. Okay? Thank you for your attention, and I will see you in the second part of this lecture.